Hello there, this is my how-to video for how to draw Lewis dot structures. Okay, so let's start with some basic facts and then do some examples. So Lewis covalent bonding generally adheres to the octet rule. There are some exceptions that I will get into later. Element and the octet rule is that elements up to period 4 on the periodic table need 8 valence electrons to fill their outer electron shell. And these will be the ones that you deal most often with in more beginner type chemistry courses. When they form bonds, the electrons are shared in the orbital and thus count for both. Okay, so here are some examples with steps. Okay, so let's say you have carbon dioxide, CO2. Okay, so the first step in writing Lewis structures is knowing the number of valence electrons in the outermost orbital of the ion, which basically you can go by the group numbers. So carbon has 4 valence electrons, oxygen has 6 valence electrons. So you have 2 of those. Okay, so then you need to know the central atom, which is generally going to be the one with the most valence electrons. But when dealing with carbon, all of the carbon's 4 valence electrons need to bond, so carbon is generally central to the Lewis dot structure, and it can bond singly or doubly and whatnot, though it will have no lone pairs. And another judge of the central atom in Lewis bonding is also electronegativity. Okay. So a lone pair is just a pair of unbounded valence electrons in the orbital of an ion, and we'll get into that a little bit more later. Okay, so for carbon dioxide, okay, so the next step is to draw the skeletal structure of the molecule. So we'll start with our central ions, carbon, and then you surround your central ion with the other atoms. So let's have oxygen and oxygen just on both sides. And so now that's done, all you have to do is fill in the bonds and then unused electrons. So carbon has 4 valence electrons and all of them need to bond. So it's going to have at least one bond here, and then since it has 4 that need to bond. So, and what this bond symbol means is that, let's say you have element X and element Y. When they bond together for one bond, each gives 1 electron. And this is symbolized right here by a line. Okay? So that's what these symbols mean. So 2 lines means carbon gives 2, oxygen gives 2. Or shares 2, because that's really what covalent bonding is, sharing of electrons. So now carbon has the octet, 8, that it needs to be stable. So, but what about the oxygens? We've only used up 2 of their electrons, so we have to fill in the unused ones. A lone pair here. And then a lone pair for the other one as well. Okay, so carbon dioxide is sort of a simple example. And it has none of the exceptions, so everyone cut that. So that's carbon dioxide. And so another one would be like, let's say, water, H2O. It's another commonplace household group, household molecule. Okay, so let's start with finding the number of valence electrons. So hydrogen has 1, oxygen has 6, who has 4, 6, and there are 2 hydrogens. Okay, so oxygen is going to be the central ion because it has the most valence electrons, and it will be flanked by hydrogen. So 1 bond here, 1 bond here. Hydrogen shares 1, it's only 1, this hydrogen shares its only one, and oxygen shares 1 and 1, and then left with 2 lone pairs of electrons. See, it's really simple. You just go through the checklist really quickly in your mind, starting off with finding the number of valence electrons, and then figuring out the central atom, the skeletal structure, and then actually writing in the bonds and lone pairs. And it's the same with larger molecules. And you just apply these same principles, and you just break them down into smaller molecules and ions, and then put them together. Like a lot of natural molecules end with OH. So you just tag that onto the end of whatever you have here, X, and then Y. So OH will have a bond to whatever over here, and then one bond to hydrogen. So it's really simple. And back to the exceptions. So some ions form the 4 standard bonds that normal ions form because they do not have the required number of valence electrons, such as hydrogen with 1, beryllium with 2, and then boron with 3. Oh, and they are limited to the same number of bonds as they have valence electrons. So, as you may have noticed previously, and as you notice here, hydrogen can only form 1 because, well, it only has 1 electron to share. And here, with beryllium hydride, beryllium only has 2 to share. So it shares 1 with this hydrogen, another with this hydrogen. And so if it was bonding in a larger molecule, well, all I have to do is remember is that it can only form 2 bonds, and double bond maybe, or just 2 single bonds. Here with borane, which is just boron hydride, BH3, boron, as you can see, is surrounded by 3 hydrogens. Boron only has 3 valence electrons by which to share and bond. So no matter what it is, it could be bonded to like nitrogen bonding to something else, hydrogen and oxygen, or what have you. And the important thing is it can only form 3. It can't just be formed like bonded to another boron or a 5th one with carbon. That doesn't work. And that's one exception to the rule. There are others, such as ions that can form more bonds than the standard 4, and a common one is sulfur, but also phosphorus. Phosphorus is very similar to sulfur, with phosphorus has 5 valence electrons. And so the way this works is if the electrons are able to move into the d orbital. So this is only possible with ions that have access to the d orbital, like sulfur, like phosphorus, obviously. And so this is sulfur hexafluoride, SF6. I'm using this as my example. See, the sulfur, even though it only has it has 6 valence electrons, and all 6 are bonded to a fluorine, as you see right here, because it has access to that d orbital by which to put the extra electrons and basically hide them into. So here it has 1, 2, 3, 4, 5, 6. So whenever you bond with sulfur or other large ions, as mentioned in the intro, beyond period 4, you really have to watch out and make sure that it's not forming even more bonds. And also with, okay, so another exception is nitrogen 2 oxide and O2, because it is possible to have a lone electron and to not have pairs, lone pairs, and these molecules and ions are made more unstable because of this, and this is called being a free radical molecule. Well, free radical ions, and which is the actual name for ions with a lone electron. So with NO2, nitrogen forms one bond with oxygen, and oxygen, as you can see, has the 3 lone pairs, and then nitrogen forms a double bond with oxygen, and oxygen has its 2 lone pairs, so oxygens are good. But the thing is, nitrogen has another electron left, another valence electron. Let's use one here, and so you have to put it in your structure, because it has 5 valence electrons. 1, 2, 3, 4, 5. And then here with chlorine dioxide, ClO2, chlorine forms one bond here, with oxygen, because chlorine has 7 valence electrons. That doesn't make sense. Cl, error, 7 valence electrons, and then oxygen has 6, so 3 lone pairs again. And then here's the single bond, so there's going to be one electron from chlorine here, so chlorine's count is at 2, 1, 2. And then this oxygen also has the triple lone pairs, so these 2. And this one bond makes a frowny face, as another 2 of chlorine's valence electrons, and then chlorine has 1 lone pair of its own, and then the last electron here makes the 7. So that's how this sort of makes sense right here. Now it's just a complete mess, but that's how ClO2 makes sense. And I'll just draw a little for the lone pairs. And so that is Lewis dot structures bonding. So I guess you could have some random examples over here. So let's have let's see, try to make something up. C2H2O4. No, let's C2H2O2. Let's see what that comes up with. I don't even know if this is a real molecule. Okay, so you're gonna have central C's, and each carbon will have 4 valence electrons. You have 2 of them. Hydrogen will have 1 valence electrons, 2 of them. Oxygen will have 6 valence electrons. You have 2 of them. Okay, so chlorine's in the mole, and so 2 hydrogens. So let's put hydrogens here, and then oxygen. So let's see what happens. We put 1 oxygen there, and bond. So this carbon has 3 bonds, and this one only has 2. So this bond needs to be a double bond. So this carbon has 4, and then so this one can also have a double bond here, so that its number of bonds goes up to 4. So the carbons have an octet, as you can see. 1, 2, 3, 4 of its electrons have been shared, and then it has received 4 electrons from the other ions. And then hydrogen is an exception to the rule. It has 2, which fills its outer orbital with 2 electrons. And then so oxygens. The oxygens now have 4 apiece, and they have given 2 out of 6, so they need another 4 to fulfill their complement and fulfill the octet rule. So 2. So now oxygen has 8, 4 here, and then 4 in the lone pairs, 4 in the lone pairs, 4 in the double bond. And so that's how you would write C2H2O2, if such a thing exists out there. O2. And if you have any questions and whatnot, please leave a comment in the comment section below. And have a good day and good luck with